I'm delighted this morning to be able to introduce Jonathan Jaquette, second seminar talk in the series. And Jonathan, if you want to go ahead and share your screen, you can get started whenever you're ready.
All right, thank you very much. Can we see the screen?
Yeah.
All right, yeah, so everybody from around the world coming to see my talk. It's a pleasure to be giving the second talk in the series. I'm going to be speaking on an overabundance of breathers in a nonlinear Schrödinger equation without gauge invariance. And this is joint work with Jean-Philippe and Lessard and Akitoshi Takayasu. And as Jay said, if you have any questions or you want to correct me for or whatever, just type it into the chat and Jay will speak your concerns. To begin, I think, let's see, there we go. So I think it's fair to say that mathematicians like problems where you can write down an explicit answer. This goes back many centuries to finding the roots of quadratic and cubic and quartic equations, and culminating in the work of Galois, showing the unsolvability of the quintic. And when we're looking at differential equations with linear ODEs, we know how to write the solutions to linear ODEs. They're going to be in terms of exponential functions, maybe sines and cosines, maybe exponential functions times sines and cosines and whatnot. But we can write these down still, even if we can't always compute the full decimal extension of sine and cosine. And also for other equations, maybe we can't write it in terms of sines and cosines, but we can write it as a definite integral, like with Bessel functions, where it's an integral of cosine composed with sine. And so if we have that we can solve like this in terms of elementary functions and integrals, we think of this as being solvable. And the sort of concept which brings this all together is that of an integrable system of differential equations, where you can give an explicit solution and it's closely linked with there being a maximal number of conserved quantities. And the word integrable comes from if you can solve a definite integral to get your answer, then it's integrable. So for the longest time, computing power wasn't really that well advanced. And so mathematicians spent a lot of time trying to find these explicit answers. And so growing out of the work of Kovalevskaya in studying the singularities in the complex plane of time of the motion of a top, Painlevé identified this property of a differential equation where if the only movable singularities in the complex plane of time, if the only singularities are poles and no essential singularities and no branch singularities, then this is said to have the Painlevé property. And this was developed because it was thought that if you have the Painlevé property, then you'll have a better chance of being integrable. And so if for first order ODEs with the Painlevé property, it's just the Riccati equation, which we know how to solve exactly. For second order ODEs, in a very nice work by Painlevé et al., they found 50 canonical forms of second order ODEs with the Painlevé property. 44 of these are integrable, and the remaining 6 define the Painlevé transcendentals. And so for our particular example of equation with the Painlevé property, let's look at this one-dimensional complex ordinary differential equation. Z dot equals I times Z squared. So here there's going to be finite time blowup. We know how to write the solution to the equation. Over here, we have our nice phase diagram. Most things are homoclinic to 0, except for finite time blowup in this direction and converging along a straight line to 0 in that direction. And it has a movable singularity, which is to say that the time at which you blow up depends on your initial condition. And so that we mean by a movable singularity, is that the place of the singularity changes with your initial condition. And also, we can write explicit solutions. This goes hand in hand with there being a conserved quantity. The conserved is 1 over z plus 1 over z bar, the complex constant. And this has itself a singularity at 0. And so the idea of an integrable system is not only for ordinary differential equations, but also in the 20th century, it was extended to partial differential equations. So one particularly well-known example of an integrable partial differential equation is the one-dimensional nonlinear Schrödinger equation. And so here we can give explicit solutions by the inverse scattering transform method. And we have an infinite number of conserved quantities. And one particular explicit solution that I want to bring our attention to is the Akhmediev breather. And so this is something where it's periodic in space and localized in time. Other times, breathers might be localized in space and periodic in time. But for this talk, I'm going to be thinking very much about things which are periodic in space and localized. Now, unfortunately, this property of integrability is not a robust one. And so one of the landmark publications by Henri Poincaré on the three-body problem was studying the perturbation of an integrable Hamiltonian. And so if you have a Hamiltonian, which is integrable, and you can write down all of the solutions, you would like to know if you perturb it just a little bit by epsilon, what are the solutions going to look like? And so in general, the series that you get from the perturbation theory will diverge through the small divisor problem. And Poincaré showed that the Hamiltonian, the energy is going to be conserved, obviously. But besides that, there are not going to be any other conserved quantities that you can write analytically in terms of epsilon, the perturbation. And so this is going to be sort of the viewpoint that we're going to be taking today. And so on the one hand, we have our nonlinear Schrödinger equations, which are Hamiltonian. And so here, if we have a nonlinear Schrödinger equation with the nonlinearity, which is written like this, in terms of some function which is in terms of the absolute value of u times u, well, this is going to be Hamiltonian. And in particular, it's going to have gauge invariance, which is to say that if we multiply u by a phase, e to the I theta, this is going to factor out of our right-hand side. And so we know by Noether's theorem that there's a correspondence between continuous symmetries and conserved quantities. And the type of equation that I'm going to be talking about today is where we break that. So we're going to break that by instead looking at equations like this, where the nonlinearity is u squared. And so we're not going to have the Hamiltonian structure. We have broken our gauge invariance. And a lot of nice properties have been left by the wayside. Now, this equation, it can be thought of as a toy model of a nonlinear Schrödinger equation where you're perturbed by an exterior electric field. The phase portrait here looks very reminiscent of an electric dipole. And here, very basic questions like, is there global existence of solutions, are answered immediately just by the homogeneous case, because we know there's going to be homogeneous solutions which blow up in finite time. And so we need to tread very carefully if we want to not blow up in finite time, because that monster is always lurking around the corner. So more precisely, what I'm going to be talking about is going to be this partial differential equation on a torus, and I'm going to consider this in the complex plane of time. And so the complex plane of time, this allows us to answer questions about movable singularities and the Painlevé property. And we know that if time is completely real, then this is our friend, a nonlinear heat equation. And if time is imaginary, then we have its more, I don't know, precocious cousin, the nonlinear Schrödinger equation. And so the sorts of questions that we want to ask, well, is there global existence? What do singularities look like? Are there many breathers? The title of my talk was an overabundance of breathers, and so you might suspect that the answer is yes. And these are sort of centering around the question of whether is this an integrable system. All right, so let's dive in. So just for the real partial differential equation, if we have a real partial differential equation where we're dealing with real time and we have non-negative initial data, then we're going to have finite time blowup. Very explicitly, we know that the blowup will occur at least by time t star, where t star is 1 over the integral of the function. And so what we mean by extending to the complex plane of time is that we can go along a contour, gamma sub theta. And so if we go along a contour gamma sub theta, which is given as such, then solving the partial differential equation can be done using sort of real time again, but just adding in a factor of e to the I theta in front of the entire right-hand side. And so this will allow us to go around singularities, should they exist. And so to give a bit of a flavor of what things look like for different thetas, here are 3 different values of theta. One is pi over 12, which is close to real time. I didn't do theta equals 0 because it just blows up very quickly. That's not very fun to watch because it happens so fast and you can't really compare with the other cases. Pi over 4, which is somewhat in the middle, and pi over 2, which gives us our nonlinear Schrödinger equation. And so as you can see, the closer theta gets to 0, the larger this is going to grow before sort of converging down to 0. All of them eventually seem to converge to 0, with the nonlinear Schrödinger equation having a lot of oscillations, very indicative of it being the wave equation. And so the first question that we're going to be asking or looking at is going to be that of proving global existence. For here, we want to prove that solutions converge to 0 for time going to infinity. And so this has some complications with it. One is that the equilibrium we want to converge to is not asymptotically stable. Okay, well that's unfortunate. Another thing is that in every neighborhood about the equilibrium, we're going to have things which blow up in finite time, which is kind of a little bit stronger than unstable. But it just means that we need to be kind of careful in how we approach this. And so the way that we're going to start off doing is by analyzing the center stable manifold for the case where it is not equal to pi over 2. So here, just to bring in some notation, we're going to be working with a sequence space. So in general, for a d-dimensional torus, we can write the Fourier coefficients of a function like so. We're going to be working with an analytic norm. Or an L1 with analytic weights. And so it has the really nice property of L1 that it's a Banach algebra, which is to say that the convolution product of the Fourier coefficients induced by just multiplying two functions together. For that, it has the property that the norm of the product is bounded by the product of the norms. And so that's what we like from L1. What we like from the analytic weights is that this gives us a large degree of regularity. The functions with Fourier coefficients which decay geometrically, as they do here, they correspond to analytic functions. And so to jump back to our partial differential equation, we take our function written out in its Fourier series. We plug in our Fourier series, taking the time derivative over here, the space derivative twice over here, squaring the function over here, by matching our e to the I omega x's. We divide through and match the terms. And so we obtain an infinite sequence of differential equations on our Fourier series. And so this is quite immediately, we throw away our partial differential equation of functions, and then we just work with our Fourier coefficients, which I am very fond of. And so the question of proving global existence now, we're going to ask in this Banach space. And so here we have a linear part over here, and we have a nonlinear part over there. And about 0, the a squared, the derivative of that disappears. And so we can just read off the eigenvalues. They're going to be minus e to the I theta, k squared, omega squared. And so we know that we're going to have one complex dimensional center subspace with a 0 eigenvalue. And the rest is going to be stable, assuming theta is less than pi over 2. And the dynamics, again, they're going to be a naught dot equals e to the I theta, a naught squared, which, again, we know this is an integrable differential equation. It's a one complex dimensional ordinary differential equation. We can write out explicit solutions to this. And moreover, using these explicit solutions, we can see that we can find a nice trapping region. That inside this half circle, solutions decay to 0 rather immediately. That is to say that this half circle is going to be positively invariant, and also the norm of solutions is monotonically decreasing, which is nice. And so to take a bit of analysis to this, we can split our infinite sequence of differential equations into a center subspace and a stable subspace. The center subspace is just the nonlinear terms, and the stable subspace, the dynamics here, and I have some exponential decay. Now the exponential decay, that is going to be related to cosine theta, and so it's the closer that we get to the nonlinear Schrödinger case, the smaller the decay is going to be. But just plotting the 0 and the first Fourier coefficient for a toy model, things will look like this, where along the y-axis with the first Fourier coefficient, things are decreasing in norm. And then for the x squared, we have this algebraic converging to 0 on the left, and then an algebraic finite time blow up on the right. And so one of the really nice things about working with the 0 equilibrium is that the entire center manifold is going to be just the 0 Fourier mode. And this is essentially because if you have a homogeneous initial data, then it will remain homogeneous, solving it forward in time. And so, I mean, the word "the" is only as unique as you can ever hope a center manifold to be. But we have a very nice description of our center manifold as just being the 0 Fourier mode. And so what we can do is we can do Lyapunov-Perron argument to show that on top of this red half circle, and not just the boundary, but the entire thing filled in, rather, we have a stable foliation by all the other Fourier modes. And so in particular, we have an open set which converges to 0. But this doesn't take care of the case of theta equals pi over 2. And so what should we do over there? So, I mean, again, if you do a numerical simulation, you see that things will converge to 0. And when we look at the eigenvalues, well, the eigenvalues, they're all on the imaginary axis. And all of them are purely imaginary. And one in particular, the 0, 1, is going to be 0. And so we have an infinite dimensional center manifold, which is quite the beast. But the trick that we're going to do here is we're going to call our explicit solution epsilon. And so now this might be a bit of a controversial thing to do, because epsilon is usually a small positive real number. And now I'm saying I want to call my epsilon something which is complex valued and changing in time. But I think that this is a lovely idea to do, because it sort of reminds you of blow-up analysis. And so what we do is, if we assume our solutions have the form the solution to the homogeneous part plus epsilon squared times the blown up coordinates for our Fourier coefficients, then we do our blow up analysis, not in the sense of finite time blow up, but in the sense of bifurcation. We match terms, things cancel, and we get this really nice equation over here for the blown up coordinates. And so here it's we have our linear Schrödinger equation over here with the I k squared omega squared. And then we have this non-autonomous, non-linear remainder over here. And this is actually very neat, because the non-linearity is decaying. Epsilon is getting smaller as t goes forward in time. And so as t goes forward in time, our non-linearity is decreasing and decreasing and decreasing. And so in order to show that things decay to 0, it just suffices to show that our blown up coordinates stay bounded. Because if this stays bounded, then our full solution will go to 0. And so I'm going to give one proof in the talk. And so if you like your moment, if you don't like proofs, well, just wait, there'll be more pictures later. And so for the theorem that we prove, we fix the homogeneous part, phi naught. We fix the blown up Fourier coefficients, phi tilde. And we assume that our blown up coefficients satisfy this differential equation where epsilon depends on the phi naught. If the imaginary part is greater than or equal to 0, so that we're in this nice little red half circle. And if there exists an r greater than 0 such that this equality is satisfied, then we're going to stay bounded for all time. And so how do we prove this? Well, we apply variation of constants. And then after we have our variation of constants, we want to take some norms. And so first we suppose that we're bounded up until some time t. And if we're bounded up until time t, well, this e to the I stuff, that doesn't care for the norm at all. That can go away. This e to the I stuff, that also goes away. The epsilon squared, that comes down over here. We use the Banach algebra property where we turn one of these a tildes into an r and the other falls down. And so recall we have our explicit formulation for epsilon. And so if the imaginary part is greater than or equal to 0, the integral of this squared off to infinity is bounded by pi over 2 times our initial condition, which you use an arctangent to integrate with, and so whence the pi over 2. And so by Grunwald's inequality, we get this nice equation over here, which by our hypothesis we assume was less than r. And so this is staying less, this blown up Fourier coefficients are staying less than r for all positive time. And so this is actually a computer assisted proof in practice. Why is this a computer assisted proof? Well, this theorem allows us to go in and ask, when are my coefficients going to decay to 0? So for example, if my phi tilde is less than 0.4, my phi naught is less than 0.5, and r is 1, then the inequality is satisfied. And so why is this a computer assisted proof? Well, if I want to evaluate the e to the pi over 2 times 1/2, well, what I do is I type it into my computer, and then I check to see whether this whole thing on the left is less than 1. And so that is why this is sort of the fundamental, well, I guess the easiest sort of computer assisted proof that we can construct. And so, well, what can we do with this theorem? Well, what we just proved is that there's going to be an open set, which we just described, which converges to 0 in forward time. And now the thing to note with the nonlinear Schrödinger equation is that if you want to reverse time, well, to reverse time, we throw a minus sign on the right-hand side, and throwing a minus hand on the right side means that this I has been changed to minus I, or just its complex conjugate. And so nothing fundamental has changed about the equation that we're studying. And so very immediately, just as we showed that an open set is going to 0 in forward time, we get an open set which originates from 0 in backwards time. Okay, which is to say, which is given as that. And so, and this is, yeah, this is convergence in norm. And so if we had any sort of conserved quantity on our sequence space, on the entire open set U, well, if it's conserved, it was going to need to limit to the value at 0, which is to say it's constant for on this entire open set. And so if it's an analytic conserved quantity, then it needs to be constant on the entire space. And this is not just for conserved quantities, but also if we had some sort of inequality, or like a Lyapunov function. Any Lyapunov function, well, it's going to start off at 0 and it's going to end at 0. And so it needs to be constant on the entire open set. And so what was really necessary in the proof that we just made? Well, the only place that the mention came up was when we were dealing with our Banach algebra and using Grunwald's inequality. And so generalizing this to a d-torus is very straightforward. If we had a more general nonlinearity, well, what we really needed to do is analyze the homogeneous equation. And the real key that we need to show is that if we have a solution to the homogeneous equation, then if we integrate the norm of this to the pth power, that this is bounded by essentially the norm of the initial condition. And we want this to be bounded because this is essentially the forcing term in our blown up set of differential equations. And so we get a very nice generalization of this theorem. So if we have some nonlinear Schrödinger equation with the nonlinearity given by u to the p for p greater than or equal to 2, real analytic f, so it can depend on both u and u conjugate, and f of 0 not equal to 0. We get an open set of initial data, which is homoclinic to 0, or a breather because it's periodic in space and it's localized in time. And moreover, if we had any Banach space, which includes the analytic functions as a dense continuous embedding, then the only conserved quantities, which are real analytic on our Banach space, they have to be constant because we have an open set of homoclinics. And so this theorem is not quite as computer-assisted proof, but for the previous version, we really wanted all the explicit estimates and the explicit formula for which we could test if conditions converge to 0. All right, so let's now take a look at the singularity structure. And so I first got interested in this project about a year ago, talking with Akitoshi Takayasu at the CRM for the month-long program for, I think, the 50th year anniversary of the CRM. And so where I first learned about the problem was growing out of the work by Masuda in 1983, where he took the partial differential equation given here and it extended it to the complex plane of time. And so as we discussed earlier, we have a monodromy principle. So if we have two paths that are fixed at their endpoints and we can homotopy one to the other without going through any singularities, then the values are going to agree at the fixed points. Now if you go around a path which is not two paths which are not homotopic, for example, if you go around a singularity, then it's not necessarily true that you're going to agree at the endpoint. And in particular, if you disagree, then you're going to have a branching singularity, which is to say that the system does not have the Painlevé property. And so in the work by Masuda, he showed that for sufficiently close to constant initial data, that there will be global existence in the shaded region, and only constant initial data will agree on the intersection. If you have inhomogeneous initial data, you'll have a branching singularity. And so what we just did with our global existence questions, well, one, Masuda only considered the real part greater than 0, so not the nonlinear Schrödinger equation. But moreover, the explicit estimates for when and where you will converge to 0, that was somewhat lacking. And so in sequel to this work is a numerical investigation by Okamoto and Shōji in 2016. And they asked the question, well, what happens for initial data which is not close to constant, such as 50 times 1 minus 2 cos 2 pi x. And so here they found that there's a branching singularity at about 0.0119. They found that numerically things seem to converge for values of pi going up to including pi over 2. And they made some conjectures about this equation. They said that they conjectured that there's only going to be branching singularities unless you have constant initial data, homogeneous initial data, and also that the nonlinear Schrödinger equation is globally well posed for any real initial data large or small. And so down here, this is the nonlinear Schrödinger equation in time, and then the norm times time as here. And so this is really largely what motivated the prior work that we just discussed for trying to show global existence for nonlinear Schrödinger equation. Now, we didn't get arbitrarily large initial data with our last theorem, but I think we did all right. And so in work with Akitoshi Takayasu, Jean-Philippe Lessard, myself, and Okamoto, we brought computer-assisted proofs and rigorous numerics to try and answer the questions by the 2016 paper. And so we showed that the initial data that they had that indeed does have a finite time blow-up, and it indeed does have a branching singularity. And this is going to occur on real time between 0.0116 and 0.0145. And so to get the lower bound, essentially what we do is we use a rigorous integrator, and we integrate as long as we can until we blow up. And right before we blow up, that is our lower bound. To get the upper bound, what we do is we take a path in the complex plane of time to try and go around the singularity. And we show that the path going in the upper half plane, that is different from the path going in the lower half plane. And since they disagree, it has to be a branching singularity. And so here we use a rigorous integrator, which I must give credit to Akitoshi Takayasu for working on and developing so nicely. And that integrator uses a Fourier series in space and Chebyshev series in time. And a lot of other people have worked on integrators for partial differential equations. And so just to briefly mention a few, using Taylor method in time work by Wilczek, Szwedzynski, Siranka, and Thomas Lanner. And so to briefly describe the approach very briefly, essentially what we do, well, first recall the differential equation that we want to solve here is A dot is equal to our e to the I theta times this. I think this e to the I theta might be superfluous over here. So my apologies. But essentially a linear part and a nonlinear part. And so what we do is for a fixed time interval, what we do is we compute using Chebyshev polynomials a finite number of the Fourier coefficients. And then we pad with zeros off till infinity. And then we define Newton, well, we set up an f of x equals 0 problem. And essentially what we want is the time derivative. We want that to equal the right-hand side of our differential equation. And so that if f is equal to 0, then we have a solution to our PDE. And so using a Newton method and a Newton-Kantorovich theorem, we define this operator T, which we want to be a contraction. We compose with this approximate inverse. And Akitoshi should be invited for a seminar, maybe explain the greater details if that is of interest. Anyway, so with our rigorous integrator in hand, we can charge forth and look at other problems. And so in the work 2019 that we did, we showed that there was a branching singularity, and that was not looking at the nonlinear Schrödinger equation. But for looking at the nonlinear Schrödinger equation, we can take our initial data and we can integrate it forward. And so if it enters our region that we have explicit bounds that go to 0, then we will have proved global existence. in forward in time. And then again, by the time reversal argument, changing our I to a minus I, we can show that in backwards time, it had to originate 0. And so in this method, we are able to get a breather, which is periodic in space and localized in time, which is limiting to 0 in backwards time, 0 in forward time, and it has this large excursion in the middle. All right, and so after taking lots and lots of initial data and integrating it and seeing almost everything going to 0, the one question that we started to ask ourselves, well, is everything decaying to 0? And so if you take some initial data, which is kind of small, you might find something that looks periodic because, I mean, it's a nonlinear Schrödinger equation. We have an infinite number of imaginary eigenvalues. Things are going to look periodic. However, when you integrate for a long time, the Fourier coefficients, they start to decay. And so here, this was the initial condition, 0.1 plus cosine 2 pi x. And after about 10 units of time, the first Fourier coefficient decreases by half. This is 0.5 and not 1 because we're missing the a, so 1 minus 1. In any case, if we decrease the homogeneous thing from 0.1 to 0.01, well, then things are starting to decay even slower. And if we take a two-dimensional Galerkin projection, and we take 0 for the 0th Fourier mode, and we integrate for 5,000 or 10,000 time steps, eventually things start to decay. And so it's sort of difficult to say whether things here are periodic or whether there can exist periodic states or if there are metastable and decaying to 0. And also, since this is an equation that does not have gauge invariance, a lot of the theory that one would like to apply is not readily available. Although, yeah. Also, an easier question, or an easier way to answer the question, does everything decay? Is instead of looking for periodic orbits, just to ask, well, are there equilibria? And so the way that we can do this using computer-assisted proofs is, again, we set up an f of x equals 0 problem. And so here, to find an equilibrium, this e to the I theta, that doesn't matter in setting set the left-hand side equal to 0. And so the function that we want to solve is this. We have our nice separation of eigenvalues. We have this nice nonlinearity. We set some Neumann 0 boundary conditions, so sort of impose a phase condition, and just throwing random initial data at it, we found some equilibria. But we didn't just find one equilibria, we found 2 equilibria and 3 equilibria. And then we started thinking, well, hey, these look kind of similar. Maybe there's a relation between them. Well, of course there is. This is a homogeneous nonlinearity. And so if we have one solution, then we can rescale it in space and amplitude, and we'll get another solution. So we have an infinite family of equilibria. And not just this, but we can also get more by finding complex conjugates. And in fact, we found 2 families, at least 2 families of equilibria. And so what's the next thing after you find an equilibrium? Now you look at what its stability type is. And so here we're solving, trying to solve this eigenvalue problem. And for the eigenvalue problem, so this e to the I theta, that can pop over to the left-hand side. And so if we find the eigenvalues for one value of theta, we can easily write down what they are for all the other values of theta. And what I would draw attention to is that this is not a self-adjoint problem, because this U star is a complex number, a complex equilibrium of this function. And so when we do our calculation and we can get computer-assisted proofs with bounds on these eigenvalues, we find that for the first one, we have one stable and one unstable eigenvalue. For the rescaling, we have two unstable, and for the third rescaling, we have two unstable and two stable. And one of the sort of frustrating parts that we have is that these all appear to be purely imaginary. However, the computer is telling us that, well, they're, I forget the exact numbers, but they're around floating point close to 0, but we can't tell whether, the real part, but we can't tell whether it's purely imaginary, it's slightly real, positive, slightly complex with positive real part, or slightly complex with a slightly negative real part. And so some more work would have to be done to precisely characterize these. But in any case, we have these nice eigenvalues which are nicely bounded away from the imaginary axis. And so the next thing, after we have our equilibrium, after we have what the stability is, at least partial answers to the stability, is we're interested in looking at the unstable manifold. And so there's some very beautiful work for doing large parameterizations of invariant manifolds, namely the parameterization method, originating to the work by Cabre, Fontek, and De La Llave. And I recommend the book by Alex Haro explaining it, and on the other authors as well. And in particular, what this allows one to do is to obtain a high order Taylor parameterization of the manifold by sequential recursive power matching. And importantly, this allows a computer assisted proof for the a posteriori error of these manifolds. And so what we did is we used a Fourier-Taylor expansion for this, our equilibria. We did Fourier in space and Taylor in time, and using, which is using the methods of Reinhardt and Mireles-James. And in this matter, using the parameterization method, we're able to get a nice parameterization of the unstable manifold here for this equilibrium and the most unstable eigenvalue. And so, as I was mentioning before, there are a couple questions or problems that you might think could come up. One is, as I said, we haven't completely determined whether there's exactly one unstable eigenvalue or two unstable eigenvalues, or maybe there's an infinite number of unstable eigenvalues. We have not resolved that in our work. But as it happens, we don't need to. And the reason being is that we don't want to necessarily, for what I'm about to do, we don't need the entire unstable manifold. We just will suffice to get the fast unstable manifold associated to the most unstable eigenvalue. All right, so now we have all the pieces of our puzzle, and we can put them together in a very nice way. So starting from our equilibrium, we can get a parameterization of the unstable manifold, and then using our rigorous integrator, we can take these endpoints of the manifold and we can integrate it forward in time. And our manifold, it has a left end and a right end, or a top and a bottom. And so we can integrate both endpoints forward in time. And then if we integrate long enough and the solution decay is sufficiently small, then we can get, and we are able to get inside of this trapping region, then we can show that it exists globally forward in time. And so backwards in time, we are exponentially running away from this equilibrium because of the unstable manifold. And then forward in time, we algebraically converge inside of this center manifold here. And so putting this together with the rescaling square, we know that we have an infinite family of equilibria. And for the first one over here, we can prove the existence of two distinct breathers, which are heteroclinic, limiting to the zero equilibrium in forward time and the equilibrium over here in backwards time. By the time reversal argument, changing I to minus I, we're able to show that there are also breathers which limit to the zero equilibrium in backwards time and the non-trivial equilibrium in forward time. And so then by scaling, this is not just for the first equilibrium, but we also get this for the entire family of equilibria. And it's not just one side is going on and the other side is going up. By doing the calculation over again, we're able to show that each stage of the each level of our equilibria, we're going to have a breather limiting to zero in forward time and also the reverse. All right, so in summary, we've been looking at this nice little nonlinear equation without gauge invariance. And so we were able to show that for an open set of homoclinics, that we have an open set of initial data, which is homoclinic to the zero solution for explicit values. And as a consequence, we have non-existence of analytic constant quantities for a large class of nonlinear Schrödinger equation. And also, we have a very nice and intricate dynamics with the far from constant initial data, with the infinite family of non-homogeneous equilibria and heteroclinic orbits traveling between these equilibria and the zero solution. And so thank you very much for your attention, and I'm happy to answer or do my best to answer any questions that you might have.
Thanks.
Jonathan. Well, that was fantastic. There's plenty of time if anyone has any questions for Jonathan.
I have, but I'm not sure. Are you waiting for writing down in the chat if we have a question, or should we just
No. Well, now that Jonathan's done talking, we can be more friendly.
All right. So I wonder. What you showed us is all for the specific equation with the U-square nonlinearity. And of course, when you do computer assistance, use computer assistance, then you always need to specify a problem. But nevertheless, one can ask the question, are these principles which you are using also possible if you change the equation? If you take u cubed or u quartic or whatever, another nonlinearity or even an exponential nonlinearity or whatever. So how much is really restricted to that quadratic nonlinearity? And maybe in the same context, or maybe, I'm not sure if the same context. So Schrödinger people always like potentials in the equation. So not just delta, but also plus v of x times u. And what of all that could you incorporate in these calculations if you, of course, switch on your computer from the start again?
All right, that's a very nice question. So I think to answer, let's see. So for changing the nonlinearity, so the work for the center manifold, I think that's decently general. You need to have the power, the u to the p in front of whatever nonlinearity, so that you get this nice dipole center manifold or quadrupole or whatnot. For the integrator, I believe it is most friendly to polynomial nonlinearities. Although I think Akitoshi could probably expound the various intricacies of what his integrator likes and dislikes. For the equilibria, we use fairly standard techniques. I would say that for the rescaling argument, that requires a power type nonlinearity. And so if you change from u squared to u cubed is also homogeneous, but in degree 3 and not degree 2. And so you'll also have the same.
But if you take u squared plus u cubed, then that breaks down.
Yeah,
right?
that will break it, correct. And then, yeah. And then for your other question, for the potential, so if you perturb the center manifold with a linear term, then that can move the zero eigenvalue off. And so then you might not have homoclinics, but you might have the splitting into two equilibria and heteroclinics going from one to the other or whatnot. And so that, I'm not confident that the homoclinics would survive a potential perturbation. But for inhomogeneous potential, for the integrator, for the parameterization method, for the equilibria, I don't think having a potential would affect it too drastically.
What?
I don't think that would be a problem.
So, okay.
So I think Ryan had a question. If you're still there, Ryan.
Yep, I'm here. Yeah, great talk. I think I might have convinced myself that this is impossible, but you have often in finite dimensions, when you have these kind of chains of heteroclinic orbits or a homoclinic orbit, you can use kind of a Linz method type approach to prove that there exist periodic orbits nearby, basically finding intersections of the relevant invariant manifolds to do so. Do you expect that to be possible in this case, or have you thought about that maybe as a way to construct nearby periodic orbits in time that would be? I know you're studying localized ones, and you might have said this. I might have missed this.
No. So that's a good question. I sort of left some leading questions that I hope people would ask. So, so one of the things with the structure here, so we have these change of heteroclinics. And so, I mean, what I think you and myself would like is that if you can go up and you can independently go down, you would like to be able to go up and then down all in one go. And the sort of problem that so the first problem that I see is that here, when we are approaching zero, we're on this top side. And when we're leaving zero, we're on the bottom side of the same subspace. And so normally, what you have are with stable and unstable manifolds is that these stable and unstable eigenvectors are orthogonal to each other. And so a slight perturbation to the stable eigenspace will give you some unstable components, and then you can fly away. But here, it doesn't seem so easy to perturb it to produce these loops as much as I would like that to happen.
Sure. That makes sense. Something to think about further.
Mm-hmm.
Great question. Other questions?
Well, there was a question in the chat by Carlos Garcia, but I guess that Jonathan answered it. But the question was, is I mean, the equation is not Hamiltonian PD in the sense that it does not conserve energy, right? And Jonathan, well, you said correct.
Yeah, so yeah, it does not have a Hamiltonian structure, and it does not conserve any, there are no, yeah, and so what we show is there's no possible way to write an energy functional on the entire space which is conserved.
So maybe I can ask another question that maybe we're hoping for. I mean, you told us about two families of non-homogeneous equilibria, right? I think.
Yes.
You have, I mean, infinitely many, but you have two which are really different. And then you told us, okay, for one of them, you can connect them to zero. What happens even numerically for the other one? Do you?
So, yeah, so for numerically for the other, we're able to get one, so our, so it also has, the first equilibrium has an unstable eigenvector. And so this is going to have two ends. And we're able to get a computer-assisted proof for one end of the manifold and linking that to zero.
Okay.
And so that one heteroclinic orbit, that will induce all the chain linking that we get, like we had before. And we're working to try and see if we can get the other end to work too. But I don't, let's see if I can share the screen again.
What you're saying is that for some reason one side is much harder than the other? Or?
Yeah, so for starters, this family has norm 20 about.
I cannot see your screen, Jonathan, I think.
Ah, no. I need to hit the share. Can people see now?
Yes.
Okay, wonderful. All right, so this has maximum at around 20. And this has a maximum around more than 200. And one end of the unstable manifold sort of decreases in amplitude initially. And the other will kind of get bigger.
Okay.
And so one is going to be harder than the other.
Okay.
Yeah, and so also, another question I'm interested in, is there connections in between the equilibria? And also, are there Km like tori near these equilibria? Yeah.
I have a second question, if you allow.
Yeah, Michael, please.
Right. So you had this picture where you showed these complex eigenvalues, where two unstable ones. I think I remember, and there are a lot of others, and you couldn't control all of them. Did you? I didn't quite get. Did you compute bounds to these eigenvalues, or are these numerical evidence? And if you compute bounds, how did you do that?
Right. So. Yes, we did compute bounds, and it was with computer-assisted proof. The way that we did this is on a torus, and so we're using Fourier methods. And so we set up an f of x equals 0 problem where we're solving for the equilibrium, the eigen vector and value at the same time.
And some normalization condition, I guess.
Yes, of course. And so, the way that we usually set this up is that the ones that we want for the eigenvalue have a sort of a radius in the complex plane. And so for any purely imaginary eigenvalue, if we have a bound that extends in all directions in the complex plane, it will spill over into positive real and negative real.
But these bounds were not enough to decide about the real part of the crucial.
Oh, so I guess if we wanted to, so the bounds that we used were just sort of the standard methods for just computing eigenvalues in the complex plane. If we wanted to impose that the eigenvalues were purely imaginary, we would need to add additional constraints.
Yeah.
But that, I think, we can do that, and we could do that for some finite number of the eigenvalues, but for the general problem, we're uncertain how one would prove that all but finitely many of the eigenvalues live on the imaginary axis.
Sometimes you can get a priori boxes or something that you can say that eigenvalues can only be in that box, but I'm not sure if that is possible in your case. That was too fast for me during the talk. Anyway, maybe I'll look at that later.
Okay, then, well, let me just thank everyone again. Say it was great to see everybody again this week, and we look forward to seeing many people back again next week. And thanks again, Jonathan. This is a high point of my my COVID week, is coming and hearing a great talk at the seminar. So.